Okay, so my name is Kenneth Tan. I want to talk to you today about resource management, efficiency, and this weird word called optimization, which can mean all sorts of different things to all sorts of different people. So just to set the scene, who's our DNS Systems? We are a OpenStack Kubernetes SAP vendor. Our aim is to enable operators to run a cloud in a flexible, scalable, and efficient manner. The agenda for today, I want to first look at this broad topic of resource management for VMs, for containers, and then we'll go into some further details. Yes, there is number of 6, and then it jumps to 9. That's because normally I'll go into a little bit more about storage and networking, and today we don't really have the time, and I'm just going to skip that. Okay? So, resource management. Now, within cloud, there is this duality of operator versus the consumer relationship. When the relationship between the operator and the service consumer are close, trusted, they have a tight relationship, then segregation and contention isn't really a problem. But when you have a situation where you do not have this tight relationship, then segregation and contention, they are key factors. So, what's an example of when you have a very close relationship versus when you do not have a close relationship? If your team is relatively small, the team being the operator side and the service consumer side being fairly small, and the enterprise tends to be, and the company tends to be smaller, you tend to then have this closer relationship. But imagine your service consumer size is a population of 8,000 people. At that scale, you typically do not have a tight relationship anymore between the operator and the consumers. Now, containers. This isn't something new. Containers, we've gone from Unix v7 isolation through the jails to C groups, and today we have containers as we see. There are two functions of containers. One is packaging system, but on the other, it's essentially a kernel slicer. So you take a kernel, you chop it up, and you segregate it some way that way. Okay. Now, for containers, when it comes to how you run it, there's a key question. If it's a kernel slicer, which kernel? Is it the host kernel, or is it a VM's kernel? Now, yep, if you're going to slice a host kernel, yes, you got to deal with a potential escape risk. Whether you say that risk is 99% or 1%, you can draw anything in between. But for the operator, this is a highly risky business. And consider that when your relationship isn't tight, operators certainly don't want that risk. Yeah. But when you're slicing a VM's kernel, for the operator, there's no risk. If you escape, you're escaping into your own environment anyway. For the operator, it's safe. The question of VM versus container, host versus VM, this is a question of whether you need live migration, whether you deal with escape, and it comes down to the nature of organization. Where you have a loosely coupled relationship, yep, you tend to then run Kubernetes, run containers inside VMs, and this allows you to have very cleanly managed segregation. Where you have a tightly coupled relationship, it could be a mixture then. Now, I know it can be crude, but sometimes another test of whether there is a tight relationship or not is, are you comfortable with sharing your porn stash? You decide. Yeah? Now, there's another view. So, when it comes to resource management, some people say, well, there is some bits of magic to then blend the containers into the right pods. Broadly, that's the concept. Yeah? Nah. Why? Because the question is actually resource management from whose point of view? Is it the operator's view, or is it a service consumer's view? Now, remember, if you're blending your containers inside the pods, yeah, great, congratulations, you can do it. But does it actually impact the physical facility? Does it actually impact the metal? Does it actually impact electricity? And that's what costs money. And for the operator, this is what matters. And so if we then come back to the matter of Kubernetes resource management, we therefore have an equivalent question. Which kernel? So if the host kernel, yeah, you can directly impact the physical infrastructure cost by right blending. And yes, it affects the operator's costs. But this is going back to the situation where you have a tightly coupled relationship organization. But if it's a VM's kernel, then the challenge of resource management really comes down to the challenge of VM resource management, because the containers running inside a VM, and then for the operator, this is a case of right blending the VMs on the host. Yeah? So our focus here is to look at the major enterprises where you have loosely coupled operator-consumer relationship, which is fairly typical in enterprises. So the cloud resource management question can therefore be translated into these two questions. So given new VM requests, where should it be placed optimally? And then as the profile of the workload changes over a period of time, how do we optimally rebalance them? How do we optimally repack them onto as few or as many servers as necessary to cater to the workload. And if we can get it right, what's the payoff? The payoff comes off in optimizing CapEx and OpEx, and you can, with the same hardware, we can therefore run a lot more workloads. And also, we can then deal with the problem of noisy neighbor. We can reduce or eliminate noisy neighbor problem. All this actually translates to cost goes down, user and boss happiness goes up. Yeah? So now, let's go back to some basics. So what constitutes cloud infrastructure? Server, storage, networking. Anything else? Not really. So infrastructure resource management is that because workloads runs on servers and storage and networking, they're only there to support. So therefore, our focus in turn narrows down to servers, servers, servers. So what makes up a server? Only 4 things: CPU, memory, disk, and network. Yeah? And today I'm not going to deal with disk and networking, simply because we don't have time. So these parts, CPU, memory, disk, and network, they are already managed by the OS. Yeah? And so let's look at KVM as the hypervisor. So now, from the host perspective, what is KVM? It's nothing more than a process, right? And yes, it provides emulation, but considering that it's a process, therefore, VM resource management reduces further into process management. So, CPU. What does Linux do? Linux is responsible for scheduling a process access to the CPU. Yeah? And when the process is ready to execute, Linux queues it in an execution queue, and Linux says the length of the execution queue defines system load. Yes? Right. And then the process is given time to execute, and it runs. And so now, when it comes to cloud, a common approach is to say, hey, I'm going to try to match the system load to some notional CPU capacity. Does it work? Or, worse, this is the absolute worst. You take a static vCPU reservation, which often comes out from your flavor definition, and then you match it to some static resource capacity. Basically, your host has certain vCPU capacity that you define. And whether it's with overcommitment or not, it's still a static figure. Yeah? So what's the problem with these approaches? So first off, CPU has many subparts. So, and the CPU is able to handle operations executing in different parts in parallel. And it can be mutually exclusive. So an example that I often use is that suppose you have 2 processors, process A and process B. Process A is pure integer. Process B is pure FP, floating point. And you have a single core processor. Both of them will run simultaneously. Linux system load says, you've got load of 2, but you've got single core. Is it overloaded or not? You tell me. So the system load view here, it really doesn't differentiate between how they are being executed and how and which part of the processor they are actually running on. And further, the CPU needs data in registers. The CPU can only operate with data sitting in registers. And if the data required is not there, it will stall and it'll fetch from higher levels of memory. Yeah? But when it's waiting, system load still says load of 1, but it's doing nothing. This is messed up. Oh, and if you have CPU heterogeneity, load of 1 on one machine does not equals load on 1 on another machine. So now, good luck in trying to match this thing up. And no, absolutely not. You cannot use the clock rates to try to give it a match. So another problem is this matter of you may have a program that's loaded, but it's doing nothing. So it doesn't require CPU. Yeah? So now, if we go back to this matter of loaded program being idle, now, tell me this. How many cores do you guys have on your laptops? 8 cores? Wow, you've got a fantastic laptop. Okay, now, on your laptop, I'm assuming it's running Linux, you type ps space aux pipe to wc minus l. Greater than 8 or less than 8?
Greater than 8.
Greater than 8.
Always.
Wonderful. So, do you have a process dedicated to a core? No. So why the hell do we manage VMs by fixing a VM to a freaking core? It's a dumb idea. And that's the fault behind mapping static allocations of vCPUs to static vCPU capacity on the host. It's a stupid thing. And to top it off, when you start your, I don't know, let's say you start a web browser, do you tell Linux kernel, I need 2 cores and 4 gigs of RAM? Do you do that? No, you just run. And the kernel figures it out, yeah? So we're now seeing dumb ideas in resource management in cloud. So now, sometimes I get asked, but what about demand spikes? Yeah, so what? You've got demand spikes also on your laptops, don't you? What happens is that the OS queues the processor and allocates the process time. And it gets handled gracefully. But what about longer spikes? Yeah, longer spikes are not spikes. They are actually trends which you can then manage. So, we are in the age of AI. We're in the age of machine learning. So why don't we do forecasting? No, it doesn't work, and it doesn't work, and it doesn't work. You want proof? See the Linux kernel. That's proof that you do not try to forecast. You look at fairly short histories, and you then allocate accordingly. Why? Because it's computationally expensive, and your likelihood of getting it right is very low. So it's much better to handle the resource requirements dynamically. Yeah. So therefore, we come to this conclusion that for CPU resource management in cloud infrastructure, it's a bad idea. It's a bloody damn bad idea to allocate based on static units of CPU and then do overcommit, because it ends up with gross wastage and terrible resource contention problem still remains. Yeah, this concept is not news. It's the concept since 1968. Why 1968? Because when time sharing was invented, and it's been dealt with that way since 1968, and yet we have 2019, and yet some folks are still telling us about, yeah, we need to fix vCPUs to the host. Yeah, right. Go and read your OS textbook. So the smarter way is that we dynamically allocate, and we do this based on live utilization for every single subpart of the CPU. So there's no CPU at all in a model. But instead, you have subparts of CPU, whether it's in the unit, it's FP unit, and you have subparts of your memory hierarchy, your L1 cache, L2 cache, and so forth. And then you do it data center wide. Basically, you apply the concept of what the kernel does in write scheduling process to the CPU resources, but you do this facility wide. Yeah? So now, memory. What do we do about memory? So you've got multiple levels of memory, and not all levels of memory are equal. And the OS will try to shuffle the data back and forth between the various parts of the memory hierarchy. And also, many people, when they write an algorithm, they assume that data fetch is elemental. So when they get an element of an array, they assume it's a fetch of a single element. But that's fallacy, because on a real machine, data movement happens in aggregate. That aggregate is whether it's in memory pages, or cache lines, so on and so forth, yeah, or cache blocks. Invariably, it's aggregate. So, we need to therefore consider based on aggregates. And another thing is that when memory is allocated, it is actually, when memory is requested by a process, it is actually not allocated. This is the reason why you can do a malloc of 4 gigs and not get a null return, even though the machine actually has 1 gig of memory. And another thing is that the kernel will actively move pages back and forth between memory and swap, and then it tries to balance the system. Yes, I know I'm simplifying this. So, in cloud, how do we manage memory? Let's go back to how much memory does this flavor say that it needs? And how much memory does the host have? And let's do some overcommitment and hope for the best, okay? That's nonsense. So what's the problem with this approach? It doesn't take into account data locality and doesn't actually realize that not all memory levels are equal. And it doesn't take into account caches, it doesn't consider that the OS will try to actively page process memory in and out. And worse, it doesn't realize that data can only be accessed by the CPU in registers. Crap. There's a problem. Invariably, this approach leads to gross wastage. Gross wastage that translates to what? Money. Money, because it's physical stuff that costs money, that costs electricity, in other words, costs money to run it. Yeah, but this is not news either. It's 1970 stuff. Yes, it was before I was born. It's handled by every single OS since 1970. So why the hell do we still do these dumb things? So what we should be doing is, again, dynamically handle memory and do it data center wide. So what this comes down to is that we need to know the data center. And knowing what happens where, why, and when, and what's the source. So we therefore need to know every single VM, what is it doing, what is accessing, why. And then we use that to write balance. And if you can do that, you can get to a minimum impact when it comes to performance. It solves the problem of catering to workloads with optimal number of servers. But in the process, what you're actually doing, what you're actually solving, for those of you who are interested in mathematics, this is a large, high-dimensional Tetris problem. And fundamentally, it comes down to the same two things. Cost goes down, user and boss goes, yay, happy. So this is one of the things that we do in Sardina Fish OS. And by the way, the name of the company came from high-density packing. That was our original technology. Okay, and today we've broadened to other parts of the life cycle, from deployment tools into day 2 ops tools, and we build this for reliability. Now OpenStack is a fantastic technology. OpenStack fantastically comes up with new improvements every 6 months. And OpenStack comes up with fantastic new headaches every 6 months. Because every 6 months, you got to bloody upgrade this thing. So we built a zero downtime upgrader for the purpose. Okay? I think we're running short on time. So give you a snapshot of some of the sites where we've implemented this in finance, operators, government sites, and IT services organizations. Most of our sites are in Europe and some in US and Asia. So, just to close off, want a job? Come talk to me. Want a free system? One free system per industry, per country, come talk to me. Okay? Wonderful. Questions? Any questions?
So what do you do about billing?
My job,
what do you do about billing
with your resource management, and specifically, what do you do about billing in a way that a mere user who doesn't understand L2, L3, L4, L5 caches understands?
What do you do with billing?
Billing.
Aha, this is a wonderful thing. So now, your users only want to know that I'm requesting for 1 vCPU, 4 gigs of memory. Yeah, that's all.
But they understand it.
That's what the user cares about. So you build a system you build a customer based on that. And so we have a billing system that by default actually bills based on essentially flavors. The same approach as Amazon. But for you, the operator, you know that a user has gone off on holiday for 3 months. This thing is sitting there idle. What? Are you going to be so dumb to leave it there? No, it's a bad idea. Let's try to pack this stuff down, and instead of having this idle bunch of VMs spanning across 30 physicals, let's see if we can pack it down to less than 30. Maybe we pack it down to 10. We've now freed up 10 servers. We can go and sell these resources, and let's go make some money. And with that, your boss goes happier. Does that answer your question? Yeah?
What happens when everybody comes back from holidays?
Yes. So now, the question of I get this question very often. So the only way that you can have a system that you can cater for infinite demands of infinite customers is to have a machine that can do infinite performance to infinite customers at infinite times, which we know doesn't exist. Yeah? So when your users come back, what you know is you know exactly what is doing, which process, which VM is doing what at which point in time. And you write balance, you write pack.
Do you know the context of the internals of the VM, or you just look the load? So do you somehow
We don't go into the VM. We only need to see from the host side, because from the host side, it's a process. I don't care what else happens inside that process. I see that process, and with that process, and I can see what resources this process is doing, and I can then write balance, write plan.
But that's a very limited view. Other question: Do you do any preempting if something goes bad, like stopping a low priority VM and start high priority VMs on top of it?
No, you don't do that. You don't stop a VM. Remember, you can't touch your service consumers' VMs. Do you want Amazon to stop your VMs?
They always do.
So the answer is you can't. So this artificial view of this concern, and perhaps often artificial concern, that what happens if everybody runs everything at the same time? Now, let's make the problem even simpler. You have one single machine, one single user. That user can run a piece of code, let's say does some calculations. Does that user ever get infinite performance? Answer is no. Okay? Any other questions?
So I still didn't get you partly addressed it, but I still didn't get what you do in case of really heavy spikes, or maybe even not spikes. Things like a customer comes and wants to mine bitcoins as fast as possible, or more realistically run an OpenCV simulation, and then goes down to being idle for a week more. So how do you handle the situation with nothing, heavy simulation, using all sorts of resources, nothing?
So I'll give you a case from a very similar case from a bank. So in this case, the application data comes in at about midnight, and it starts cranking. And it finishes about 7 o'clock in the morning. By 8 o'clock, the application is pretty much idle. And it stays idle for the next 2/3 of the day. So, if we were to build a machine fully dedicated to this one single application, that means we have a machine for which we're burning electricity 2/3 of the day for nothing. But rather, what you can do, even if this machine is only catering for one single application, is that what we then track the actual utilization of the VMs. Come 8 o'clock in the morning, it starts to idle. So you know that resource utilization is rapidly decreasing. You can then start packing. After you pack, what do you do with excess machines? In the case where you have a machine built for one single application only, put the machines down to low power mode, turn them off. In other words, you're no longer burning money. And then, come midnight, data comes in and they start cranking. Yeah, and because you're on the host side, you detected this. You can then start to spread them back out. In the process of spreading them back out, you power on machines. You bring machines back to active mode. And by the time it gets fully spread out, in their case, it ends up with one VM using full resources of the machine, and there's no contention.
So do you do only horizontal scaling, or do you do also vertical scaling?
What do you mean by vertical scaling?
When you add resources to a single VM and not adding more VMs to the system.
I don't understand the question.
You can add, so it's possible to add more CPU cores and more memory to a single VM. That's called vertical scaling. And it's possible to add more VMs to a system. That's called horizontal scaling.
I'm on the host side.
Yes, but you can configure the VM, so you can add more memory to a VM.
Yes, that's the view from the VM side. From the host side, I only see what you're doing in the FP unit, what you're doing in this unit, etc., etc.
But still, you control the resources of the VMs.
Yes.
So you don't dynamically change the VMs to allow them to consume more. You have your flavors which are more or less set, right?
Yes, but we don't manage resources based on flavors. That's the key.
Okay. And to do horizontal scaling, you need support from the applications.
That's not my business. That's the service consumer's business.
Okay. Uh-huh.
Service consumer starts more VMs, that's their business. And equally, if service consumer wants to increase number of vCPUs for the VM, that's their business. But from what I see, it's what they do on actual metal.
It's even a comment, no? Another question. You could probably allow users to provide you some hints on how they use data. Or, for example, in case of this spikes, like,
Yeah.
okay, from 12 p.m. to 8 a.m., I'm going to crank. And then you avoid the cost of live migration when you only realize that they are actually killing their neighbors and you have to live migrate them to a new machine, which you have to power on, which can take 10 minutes.
Okay, so there are 2 points here. So you can set up the system so that you have some buffer machines. So if you can say, I have 10,000 physicals. At any point in time, I'm going to keep 10 as buffer. So if I can pack the entire workload of 10,000 physicals down to 100, my total number of machines powered on is 100 plus 10. So I have that buffer to very quickly flow into. But and then hopefully within that 5 minutes, 1 minute, 10 minutes, whatever the amount of time, I have enough time to bring up additional hosts. Now, there's another very interesting case, which is that if you have, and this is particular for for a certain type of operators. So the operator needs let's say 1,000 cores dedicated for a particular user group between 12 o'clock and 1 o'clock every day. Only that. Yes. Yes. We should let them in.